Hi, everyone. Good morning. Today, I will talk to you about spatiotemporal understanding of the built environment using visual data. Specifically, how can we build 3D spatiotemporal maps of our changing environments? Okay, I hope this is better. So this is a construction site for those that have never seen one. And as you can see, over time, many layers of semantic information are being added, right? So you start with the outer shell of your building, and then you start adding information such as insulation, pipes, cables, other walls in the interior design, etc. And given the fact that we want to reach sustainability goals and circular economy goals, it is very important to understand where are things located in this building, what are they, how are they connected with other elements, what material are they made from, etc. And this is something that today we're not doing very well. We have issues with construction progress monitoring to understand when things are and how they change over time. I will give you a few statistics just to a little bit understand how important this problem could be. Okay. Is it still visible in Zoom?
No, you don't have to share it.
Okay, sorry about that. So statistics have shown that 50% of the construction cost increase comes from reworks, which mean things that we have not built the way they should be built. Maybe it depends on quality, maybe it depends on last minute changes, maybe it depends on clashes between different expertises. So I ideally would like to be able to minimize that in order to have more correct construction cost estimates. In addition, I want to point out that we do have a lot of fatalities in the construction industry. So this is in the US. For 2020, we had about 20% of the fatalities were actually for construction workers. However, if we are able to understand what are the causes of these fatalities, understand which activities or which elements that we are placing are causing mostly these injuries, we might be able to have less people dying in constructions. And in addition, with respect to sustainability goals and circular economy goals, we need to understand that 95% of the materials we are using in construction sites could actually be able to be recycled for either other constructions or other purposes. Something that right now we are not really doing with our buildings when we are demolishing or renovating them. So let's see how spatiotemporal understanding of the built environment of these construction sites is happening today in the field. So you will build a construction timeline, where at time t you will get a laser scan of your space. And these red dots that you see on the screen are essentially laser scan locations. And then at time t+1, you will get another laser scan, and at time t+2, another laser scan, and so forth. And now the goal here is, in order to be able to understand how a space was constructed and how it changes over time, you want to be able to make the spatiotemporal associations across the scans, right? So you want to be able to understand that this corner over here is the same as this one over here and this one over here to start making this analysis. And this becomes easier once we are able to align all these scans that we have in the same coordinate system, right? However, this is not a trivial task, especially if we consider that we want to address it without the use of georeferencing information or any kind of markers. In addition, we are talking about construction sites, right? So why it's not trivial? Because they change so much over time in their geometry, in their appearance, and in their topology. In addition, during construction, not all areas are accessible to us over time, right? Which means that every time we go to do this new temporal scan, we might not have access to everything. And finally, there are ways in the way that the reconstruction will work for each of these temporal scans that we cannot always get the same exact geometry. So the very first step in being able to make this spatiotemporal analysis is, as I said, to align everything the same coordinate system, known also in the computer vision as the spatiotemporal 3D point cloud registration task, where essentially given 2 point clouds, the blue and the yellow, let's call them fragments because these are individual laser scan locations essentially. You want to be able to identify pairwise correspondences from the static parts of the scene while ignoring temporal changes. Let's look now into what exists in the literature. Can we find datasets that have these large geometric changes? And are there any methods that are able to address this? In short, let me tell you that there are no datasets that have these large geometric changes that we see in the construction sites. They are more about moving a chair around or adding a table in the room. And as for methods, most of them focus on the spatial registration tasks, essentially no change in the space. And those are essentially also applied to the self-driving car domain. And the reason that they work for this domain, although there is some temporal change, it's because the main structure of the scene remains unchanged over the different temporal scans, right? When you have the self-driving car going around, a few seconds later, what would have changed is that maybe a car has appeared in the scene, a pedestrian might be crossing somewhere, but the main structure, the roads, the buildings, the trees around will have remained the same, except if a big natural hazard has occurred in the next few seconds. So the goal here is we don't have a data set, so we need to find a data set. And then can we see if existing methods that are able to solve the self-driving car spatiotemporal problem actually solve the construction site problem? And in order to do this, we developed with my collaborators, Nothing Stands Still. And we borrowed this name from the Greek philosopher Heraclitus, who said that nothing stands still and everything flows. So we collected a data set from construction sites that are very large and demonstrate these changes of geometry, topology, and appearance. And we are using it as a benchmark for existing methods to see how well or not they're doing, and also offer it to the community in order to build better methods that are able to solve this task. But in addition, the dataset can be used for many, many other tasks, being that robotic or perceptual ones, and you will see later. So let me introduce to you how we build this benchmark. This is the flow of how the tasks would work. So given 2 fragments that could be from the same or different temporal points and have some spatial overlap, an automatic method will try to register the pairs of fragments together. So you would get this kind of pairwise alignment. And after you complete the pairwise registration, what you want to do is to create the big spatiotemporal map with all the possible fragments you have in your hands, right? They could be from the same temporal point, from different temporal points. You want to create this big spatiotemporal point cloud. And in order to do that, you perform the multi-way registration step, where you initialize it with the information from the pairwise alignment. Chapter number 1, how did we capture the data? So this is what the dataset looks like. In contrast to the previous speaker, that we saw a lot of excavation or foundation. In this case, we are looking into the main structure of the building being erect, the outer shell essentially, and now we are going to see how the interior construction changes and how we are building essentially rooms, we are adding insulation, pipes, etc. And these are the 6 areas we have in our data set, and we have different temporal points that we acquired from them. Here you can see some zoom-ins and snapshots and crops from these data sets. And I want you to focus over here, where you see how we begin from an almost empty space, and then we start adding all the construction elements, and material moves around, machinery moves around, etc. How we generated the data set. So we collected these point clouds with the Matterport camera. Essentially, it's an RGBD-based tripod that you move it around into different locations. Because the output of this sensor is the RGBD reconstruction, essentially the reconstructed mesh of that space, we need to somehow be able to get individual fragment out of it, essentially these individual point clouds. In order to do that, we are going to use a simulation environment, and we are going to try to replicate as much the natural real-world setting. So the first thing is to see where can we place our scanner in order to get these fragments. And in order to do that, we used each of those meshes and we created a 2D probability map of where it's higher chance to place your scanner. And in this specific example, you can see the whiter the pixel on the map is right now, the more probable the location for putting the scanner on. And then we sampled many, many, many locations, as you see here. And as I said, we did follow the real world setting of how this device would work. So essentially how much distance you could place in between the scanners, etc. And so now we have many, many possible scan locations, right? The next step is to actually generate those RGBD, those point clouds around you, those fragments. This is how the Matterport camera looks like for someone who is not aware, and it has these 3 RGBD sensors and rotates 360 degrees around its axis in order to capture depth in 6 individual locations, right, in 360 degrees. And then you get these depth images and you can stitch them together in order to get this and project them in the 3D space to create this simulated point cloud. We also added statistical noise based on the specific settings of the camera sensor in order to be, as I said, as more real world as possible. So now we have scan locations. We can get individual fragments per scan location. What is left? What is left is to actually create the input for the benchmark, right, for the methods. And let me show you over here, right, remind you, that the input is 2 fragments, right, a pair of fragments that have some spatial overlap from the same or different temporal points. Now, how can we create this data set, given that we have multiple scan locations? How can we create the combinations? The combinations become a little bit intractable and the size becomes too big. So what we have to keep in mind is that we are dealing with deep learning methods mostly, right, these days, which means that we want a large size data set. However, it has to be diverse in order to allow as much generalization as we can out of these algorithms. So we decided to use 3 metrics in order to understand which would be the most suitable pairs to use in our dataset. The first one is the overlap ratio. It's a standard metric used in the spatial registration domain, where essentially you want to understand how much 2 fragments overlap in space, regardless of whether they are from the same or different temporal points. Now, we also devised a metric in order to understand the temporal change, because that is also an important factor to make sure we can have algorithms that can learn how to do the temporal registration, right? So in this case, we just measure how many points in the overlapping region have changed or not. And I would like to give you an example of these 2 metrics before I go to the final one. So here you see 2 examples of 2 fragments that overlap. The yellow and the blue are the point clouds. Green and red are in the overlapping region between these 2 point clouds. Green are static points, red are points that have changed over time. Computing these metrics, overlap ratio is the same for both of these examples. However, the temporal change ratio is different. And you can see that although in the first example, it's not that big of a value, in the second example, we have more than almost 60% of the points being different between these point clouds. And why is this a challenging task? Well, if you have a small overlapping region, then you have way less points in the static parts of the scene where we want to find the pairwise correspondences. And given also how we are trying to find correspondences that are essentially more distinctive in the geometry within a local region, you understand that if you have only 40% points that are static, and we are talking also about construction sites where the geometry cannot always be very distinctive, we are going to have a very challenging task to solve. And this is the final metric, that of geometric complexity. So we don't always only want things to have different spatial overlap, different temporal changes, but we want also to make sure that we have point clouds that are flat and bumpy, right? Somewhere in between these 2 ranges. Let's go into the pairwise registration tasks and see some benchmarking results. Over here, you can see results for the original dataset split. We have 2 more splits. The original is that follows exactly the spatial registration with no temporal changes standard setup, where essentially, given, for example, the 6 areas that we have in our dataset, these big bounding boxes, and the different temporal scans that you can have per area, these black circles, you want to sample, train, and test data from all these different temporal scans and areas However, of course, they're not the same exact duplicate data, but they do belong to the same area. So this is the standard setup. We have two more splits. One is to understand generalization over different scans. And the second split is to understand generalization within one area over time. So can we learn from the beginning and then be able to do more in the future for the same area? But I will show you, for the sake of time, only the original split today. Here you can see the different methods that we tried. The first one is a very traditional one based on the more handcrafted features, and the rest one are deep learning ones, with predator and geotransformer being the state of the art right now in pairwise registration for the spatial task of registration. You can see that the methods are not performing very well. If you take into account that, let's say, predator and geotransformer perform 90% plus in the existing spatial registration tasks, we see that there is quite a big gap here with respect to the spatiotemporal task. It would be interesting if we'd ablate these results in order to see where do we gain most in the performance. Does it come from the spatial registration task or from being able to temporally register the point clouds? And I guess, as expected, the main gains come from being able to perform the spatial registration task. As you see, predator reaches 90%, almost more than 90%, which is exactly what we would expect for the spatial registration task. However, in the temporal task, we see that we have about 28%, and then the rest of the methods go really, really low. You see the handcrafted one barely is able to register anything. Again, this is, sorry, I didn't mention, this is registration recall, which essentially tells us which percentage of the data has been able to be registered correctly within a certain threshold of distance between the points. What does this tell us? That we need to be able to develop better methods that are able to perform this task for large geometric changes that has happened over time. This is not only important for construction, it's also important for computer vision tasks, given that these days we have on our phones these LiDAR scanners, and who knows what will happen in the future. We are constantly collecting this data. And if we want to be able to create spatiotemporal maps of our world within small or large geometric change that has happened, it would be ideal to have methods that can actually perform this registration, right? In addition, this kind of data is a very challenging setup for the computer vision community, given that we are talking about spaces with low, usually texture, and also very repetitive geometric structure. So as we understand, this become a very challenging scenario that if we build methods that are able to solve this, we could potentially assume that they can solve every kind of setup as well. Here are some visual results of the pairwise registration for the 3 best performing methods on this task. And you can see how indeed predator, who is the one who performs the best, is able to register closely to the ground truth. This is the same exact area with and without ceiling, so you can also see how the geometry of the ceiling looks like. And this is one failure case that is actually a failure case in both you can understand that it would be a failure case in both the spatial and the spatiotemporal registration task, given that we have 2 rooms that look very, very much alike in geometry, maybe a little bit mirrored, but still they are very much the same looking. And in this case, all methods fail to be able to register them correctly. Final chapter, the multi-way registration. Where essentially so far we have been able to register 2 fragments together, right? 2 individual point clouds. Now we want to take all the point clouds we have and create this big spatiotemporal 3D map out of it. What we do is we use an existing method that performs multi-way registration, which essentially forms a pose graph that is going to be optimized based on the weighted RMSE between the nodes. And what is a pose graph? It's a graph that the nodes are all the individual fragments that you have, and there is an edge between them if you have some initialization about the pose between these 2 nodes. This is how spatiotemporal graphs look like in our setting for the test set. Here is another case. There, just see how dense they are, right? These are the results. As you can see, we have the top two best performing methods, predator and geotransformer. You see there's a little bit of a conflict. Some are going up, some values are going down, right? Here is with the pairwise registration results. Here is after the multi-way optimization, the multi-way registration. And here is the difference between the before and the after. And in some cases, we see that we have we do not have an improvement. We actually make worse the scores. And the other case, we see that the scores are becoming better. Ablating these results for temporal and non-temporal cases, we again see that the results are fluctuating. And I want you to consider for this specific case, the reason it's because for the pairwise registration, current methods have an objective of increasing the registration recall because they are dealing about finding the best correspondences that they can, and they don't really minimize the RMSE between the two fragments, versus the multi-way registration method that is the state of the art right now. What it does is it minimizes the RMSE. So we have conflicting objectives, and as such, it is harder to be able to say which one performs better or not. Again, this means we should develop new methods that are able to solve this task in a better way, potentially having common objectives. Lastly, I want to show some qualitative results before I wrap up. Here you can see for this area, this is a ground truth. The different colors mean that the point clouds are from different temporal points. And then it's a hue. The blue ones are from one temporal point, the red ones are from another, and the yellow ones are from another. So here you see the results of building this spatiotemporal map over the entire area just by considering the results of the pairwise registration, and here after the multi-way registration. And I want you to focus on these particular areas here, these shafts. You can see them here on a close-up. Before the multi-way registration, things are very unclear, but once we do the multi-way registration, everything becomes way more organized, and similar for the other side as well. However, this does not always work. This is the example I showed right now. You can see just in the different temporal stages that are 6, how this scan looks like before and after multi-way registration. And here you can see that after the multi-way registration, we have been able to improve the results. But in this case over here, you see that actually the results are very bad. And this is also because when you have such a bad initialization over here, you can barely recover afterwards the pose. So this is another reason why the multi-way registration doesn't always improve. Okay, I want to bring back this kind of benchmark and motivate it with respect to construction one more time, because it already allows to create a timeline, an as-built timeline of your method over multiple times. And it also enables construction progress monitoring, where you can do better quantitative analysis and qualitative control. As a coming up next step for this data set is that we're going to provide semantic annotations. We are already working on that, so we can perform many, many more tasks, be that perceptual, robotic, etc. These are my collaborators, and I want to thank them so much for being part of this effort. And finally, I want to tell you that we are going to be presenting this work as a CVPR demo. If you come to CVPR, please join us to find more about this data set, discuss how you could use it for your own tasks. Right now, it will be everything available by the end of June, like by June 23rd or whenever the demo will be up. For now, you will see that the website is also under construction. That's it. Thank you very much. Any questions?
Hi, thank you for the presentation. This data set is going to be extremely useful for all of us working on the field. I don't know if it's bold to assume that we are going to have the main information always, but do you think that could probably solve some of the issues we have with the spatiotemporal registration, in the sense that if we have the main information, we could probably just focus on the structural components that are going to allow us to register the pairwise registration, and try to remove all the clutter that is going to just add noise to the registration?
This is a very good point, a very good question. I see a few challenges there, though. First is you have to localize yourself with respect to the BIM. The second one is that notoriously, for some reason, we cannot build the way we design, so there are going to be changes. So it might be harder to understand if the change comes from being clutter or because we just build the same thing in a different place. And the third challenge that I see is that we don't have building information models that kind of follow a bit the construction progress. So you might be removing something that's supposed to be an element, but just because it's in a very different shape, form, or potentially even location yet, you might just discard it as information. However, if there is enough, then given all these three challenges, I think it could help to remove some of the clutter. However, I don't know, in a realistic scenarios for all possible machines to have building information models that are nicely constructed that can be used, I think it's more of a challenge than actually solving the perceptual task with the clutter in there. Yeah.
Hi, I'm really interesting data set, so thank you. I had a question about if you have these full 3D maps of the entire environment, why are you trying to match individual scans? Why not match, say, a larger area? I think that would make the problem perhaps easier.
It's up to researchers coming up to being able to solve that task if they want. The way it usually works right now in the literature, and that's why we created this benchmark, right, to enable that. The way it works right now in the literature is that you need to have some initialization of the pose between the point clouds before you're able to perform the optimization of the entire map. So you need the initial alignment with the 2 point clouds to perform the entire map. Consider that you just have a bunch of boxes, a bunch of pieces of a puzzle that you have no idea how to put them together. It's going to be way harder to try to optimize everything simultaneously instead of starting doing these small connections. I have a piece of puzzle here, this one connects, yay, I have another one and start creating this puzzle, right? However, I do not see it as something that cannot be solved in the future. Hopefully, people will use the dataset to do that.
Okay, thank you.
Thanks for the presentation. I had a question about choosing the hardware. So instead of choosing a tripod, stationary laser scanner, why didn't you choose a, sorry for that, a SLAM-based laser scanner?
Yeah, very good question. So I have a couple of different answers for that. The first one is that we collected this data back in 2018 or something. It took us quite a while to be able to reach this point where we're going to present it to the community. So back then, other systems that are more SLAM-based and with laser scanners were harder to find and potentially even more expensive to use. This is a low-budget scanner, which allows people in construction sites, if they want even to do a quick understanding of the scene, to use that. However, I don't think that this method is necessarily or this data set is constrained to a tripod setting. Of course, we will make available to the community the 3D meshes as well. And one can use a similar simulation environment. We use Blender to collect all this data in order to collect bigger, potentially SLAM-based point clouds. The point is, how can you still put everything together, right? You will still have the same problem over time to register all the point clouds together, or even if they're of big areas, or even you are just even with SLAM systems, you might be getting certain areas here and there over time, right? Not the entire scene. So still the same problem applies. But you're very welcome to create a different version of data that are more SLAM-based using the 3D meshes that we're going to provide.
Hey, thank you for thanks for the great presentation. My question is, so far, from my understanding, the matching between fragments is agnostic from the classes you assign to point clouds. And you just said that you're going to provide soon a labeled data set for semantic segmentation. Is it used after the matching? Is it going to use be used after the matching, or are you using the semantic labels to improve the scores you have right now for matching the fragments?
A very good question. So a clarification, we just showed existing methods, right? Not our methods for all these steps is the benchmark to understand the state of the art, what it's doing. We are already kind of have developed a method ourselves, which is not published yet and not available. But this is, again, only geometry based. However, our plans is indeed to be able to perform semantic registration, spatiotemporal registration, where we are going to use the semantic information to hopefully inform the registration task, but also vice versa, to be able to use the registration, the geometric registration, to improve the semantic segmentation. That would be our goal.
Okay, thank you.
Thank you.
And I have another question
Sure.
regarding the computational power needed for this kind of method. So once you collect all these fragments, so I suppose these 3D point clouds have occupy quite some memory. And how much memory do you need approximately when you build this huge pose graph to match the fragments?
Right.
Or what kind of hardware do you need?
I mean, we did use, I think we used just one GPU in order to perform things, and not the highest end, but one of the higher end GPUs.
Thank you.
Supposed to be.